Hey everyone, so here's a fun one. Question 45 of the practice final. We have Cecily, a speed skater. So she's speed skating. Her mass is 60 kilo. She's gliding forwards, northbound on ice at 10 meters per second. So again, just as always, it's great to have a free body diagram. There's her speed skates, nice and long. Her hands out. There we go. Um, right, so again, mass, we know she's 60 kg, and we know her velocity, so she's moving forward at a, let's see, 10, actually we can probably pick a better spot. It's not quite a free body diagram, so that one is at 10 meters per second. So that's her velocity equals. Okay. What's up next? The friction acting on the blade of her skate is 1 Newton backward south. Yeah, right. So we forgot to put that here, didn't we? So that's north, this is south, and that's just another way of saying like positive or negative, or forwards and backwards, all the same idea. But one thing that came up here in the question is friction. So with friction, again, didn't specifically cover it per se, but it's essentially a x-axis force, whereas normal force is typically vertical or perpendicular, sorry, to whatever the surface is. So this is a parallel one. So even if we didn't know that, even if that was information we didn't cover in class, doesn't matter. This question gives you all the information you need. So you know already that there's at least 1 Newton of force working backwards on Cecily here. Okay, so that's that taken care of. Air resistance creates 5 Newtons of force, also acting backwards or south. So again, normally we'd be drawing this from wherever the force is being applied. It's uniformly air resistance being applied across the body. You know, if we were to draw this one correctly, it would have been from the skate, because that's where the friction's occurring. Well, that's okay. I wanted to do this to try to illustrate a point. So we have 5 Newtons also acting backwards now. Great. If these are the only horizontal forces acting on Cecily, what is her horizontal acceleration as a result of these forces? Okay. So again, looking at this, we can just think about force and take a little peek here at our equation. Well, force equals mass times acceleration. This is known, right? So do we have a mass? Yeah, we have a mass. Do we have acceleration? No, so we don't really know that. But we do have a sum of horizontal forces. So what we can do is we can figure this out. Yeah, we can rearrange and figure it out, okay? So first of all, let's sum up all our forces. So what do we have? Well, we have that 5 Newtons of air resistance. We have 1 Newton of ice to blade resistance, or frictional force occurring. And from there, that's it. So before you're like ready to throw the 10 meters per second in there, that's not a force, right? So again, we can have a velocity that's non-changing. And if we don't have a force that's changing, or sorry, a velocity that's not changing, essentially what we have is no acceleration, in the sense that there's no changes occurring to the system. But that being said, this is velocity, not acceleration. Okay, what we're trying to find is the acceleration. Okay, so all we know, all that the velocity is telling us, is that we just have a moving person or a moving object. Okay, so from this point in time, we'll see that out of the whole kind of free body thing, as far as our horizontal components are concerned, the sum of the force x, x components, is we have 6 Newtons. And yes, that's working backwards, we want to keep track of that. So you can probably put south just to keep that in mind. Okay, great. So now we're going to revisit our force equals mass times acceleration. And we'll notice that we're not solving for unknown. We're not solving for acceleration yet. Okay, so if we rework the equation, and there's this kind of cool trick that I'd recently been reminded of from a student, that if you make a little whenever you have a menagerie, or if like a mix of like three variables, what you can have is you can go force, so what it equals, times mass, or times acceleration. So mass times acceleration equals force. So you can look at this a few different ways. You can say, okay, force divided by mass equals acceleration. Okay, you can go force divided by acceleration equals mass. Or we can do the one that we know, and it's mass times acceleration equals force. Okay, so a little helpful triforce of variables there to kind of help you navigate how to rearrange three variable equations that look like this. Okay, so two multiplications equals one variable. Okay, two multiplied variables. Okay, so let's move forward. So using this again, we want to figure out acceleration. So we're going to say, so force divided by mass, right? That's what our acceleration is. And let's double check, make sure we got all our variables before we keep barreling forward here. Do we have forces? Yeah, we got our net forces. Do we have a mass? Yeah, we have a mass. We already established that. So we should be able to figure out her horizontal acceleration, and that's all we're looking for. And again, that's a result of all the summed forces that we have. So if we take all our 6 newtons, again, you can put south, negative, whatever. I think just for ease, what we'll do is just carry that along just so we know that's there. And our mass is 60 kg. So what's our ultimate acceleration? Well, 6 over 60 is 0.1, and that would be, because it's an acceleration, meters per second squared, and that would be southward, or again, depending on how we had our system set up, positive or negative. And we can just look back now. We can say, okay, well, positive was forward, negative was back. We know these forces are backwards, and so we can say negative. So we can actually say that this acceleration is actually a deceleration, okay, based off of what we found here. And that makes sense if the only two forces are frictional and air resistance, or they're gonna be slowing her down unless she was applying force to move herself forward, right?